Hello and welcome to my poster pitch video about fractal analysis for characterization of ultra-short pulsed laser textured surfaces, enabling machine learning powered categorization. The motivation of this work arises from the problem that ultra-short pulsed laser treated metal surfaces create all complex and hard to describe micro and nanometer structures, and many laser and process parameters resulting in vastly different surface topologies. Finding and reproducing those topologies tend to be very time consuming and have to be done every time for each laser material combination. Topography without math or geometry-based metrics is only describable in qualitative terms. The idea starts by manufacturing a dataset of topologies and libs across all necessary laser and process parameters using a multi-parameter matrix, followed by automatic measurements on all machined surfaces with a 3D laser scanning microscope. The characterization of surface topologies are done by fractal analysis with box counting, lacunarity and profile roughness parameters, and the calculation of the surface processing rates. Processing the data after saving it into a database with clustering of topologies only with fractal and profile measurement data with a suited algorithm, and statistical analysis of the found classes gaining knowledge about the needed laser and process parameters. If you got questions about the experimental setup and the state-of-the-art enabling this methodology, I welcome you to my exhibition stand and let's chat about those things. The process execution is as follows. First, we laser machine a multi-parameter matrix onto a metal surface. Afterwards, the 3D laser scanning microscope is measuring every parameter combination automatically. Afterwards, we process the data by cleaning and ordering the parameters and saving it into a database. The execution of the fractal analysis and saving the results into a database results in being able to cluster the data points while using only topographic data. In the end, statistical analysis answers the question what parameters are necessary to get to the desired surface structure. Here you can see the machine 3-stage multi-parameter matrix, resulting in 9,600 parameter combinations at a specimen size of 5 by 5 centimeters, containing the parameters of the number of scans and the machining angle in stage 1. The stage 2 handles the pulse distance and the line distance, and the stage 3 handles the laser fluence and the pulse repetition rate. Coming to the results, described by the discovered clusters and the statistical analysis. By specifying the number of clusters to 8, a satisfying result could be obtained, and the number of clusters are ordered by the magnitude of change compared to the initial surface. These clusters can be statistically analyzed by different metrics. The database is, for example, now searchable by the surface processing rate. One example is to sort all parameters from one group by the fastest surface processing rate, or enabling approximation of the mean surface processing rate for a specified topology, which can be important from an economical standpoint. The second metric being the fractal dimension, while a high fractal dimension correlates with a high roughness on many scales. The fractal box counts enable sorting by spatial complexity, or similarity search between wanted structures and the database contained structures, finding optimal parameters. The lacunarity enables anomaly detection, which comes in favor of troubleshooting when searching and sorting for highest lacunarity, resulting in errors like dirty specimen, destroyed, cracked and damaged specimen, incorrect measurements, also partially mismeasurements and fully unusable mismeasurements. The variation of lacunarity enabling further searching possibilities. On the left you can see structures from the large cone cluster. The first image is the result when searching for minimal lacunarity in this cluster, resulting in a little cone structures, while the second result is while searching for maximum lacunarity in this cluster, returning a topography with very large cone structures. The third picture is when searching in cluster 5, ripple without grain boundaries, with a minimum lacunarity resulting in a very homogeneous surface finish. At last, statistical parameter analysis enables that we can find out what general parameters are necessary to create this kind of structure. And by sorting these structures by the surface processing rate, within one group the fastest parameters are returned to maximize economics. I hope you found the video and the included methodology interesting, and I would be glad to chat with you about its details. Thank you.